Okay, so the plan for today is to start on 6.4, and then the supplement on 6.2 to 6.5 will be posted in the next couple of days. And I didn't post 6.2 and 6.3, by the way, because there just wasn't a whole lot to cover that we didn't get through in class already. So I'm just lumping that in with the supplemental work in 6.4 and 6.5. So section 6.4 on work, the physics concept of work. Super interesting concept, super important concept. If you you can look into things like the work energy theorem and so on. Very important ideas, work, force, and so on, relating to basic physics and more advanced physics. So what is the physics background of the idea of work? So first, Newton's second law says that force equals mass times acceleration, and we're going to be working in scenarios where Newton's second law applies, easily and directly, and there are no extra complications. So F equals ma is kind of our starting point. F stands for force, m for mass, a for acceleration, and s for position. We often use s for position because p is kind of already taken by momentum. So s, or sometimes x, is position as well. The SI units for these, the units of force, are newtons, units of mass, kilograms, units of acceleration, meters per second squared, and 1 Newton is 1 kilogram meter per second squared. In other words, a force of 1 Newton applied to a mass of 1 kilogram yields an acceleration of 1 meter per second squared. The imperial, or the kind of American unit of force, is pounds. Sometimes it's written as pounds force, like LBF, as opposed to the similar sounding, like pounds that can also be used for mass. It's, I don't know, our system of units is kind of crazy. So, but here we're thinking of pounds force. So we're thinking of, like, if you stand on a scale, that gives you a unit of force. It's mass, like how much mass there is in your body, times acceleration, times the acceleration due to gravity. And then in the algebraic structure, in the kind of nice discrete structure, work is force times distance. So if I apply a force over a certain distance, over a certain length, the work that I've done is the force that I applied, the constant force I applied over that distance, times the distance over which I applied that force. The units of work are force times distance, or newtons times meters, or Newton meters. And 1 Newton meter is a joule, Joule. Or in the American units, the units of work are foot pounds or pounds feet, depending on kind of the context. Sometimes it's pounds feet for things like, say, torque, or foot pounds for work. And that's about 1 foot pound is about 1.36 joules. Okay. We won't be worrying too much about all these conversions and everything, but one thing that I think is a very good practice in certainly in physics or chemistry or whatever, but also in math when we have application problems like this, is if we keep track of our units, newtons and meters and so on, we can make sure that everything at the end is phrased in the correct unit. If we get to the end and we're saying that work is 27 newtons per meter or something somewhere went awry, and we might want to go back and review our work. Maybe we set something up wrong. So by tracking our units, it can serve to check our work. Or if we aren't quite sure how to set something up, by doing dimensional analysis, by focusing on the units, that might give us some clues as to what pieces go where. So that's another way we could do it. If we, forget a little detail or a formula or something, maybe we can get a hint by, maybe if we know what units we should end up with, maybe we kind of can make a guess as to what things ought to multiply together. that's obviously not super scientific, but you could use that, and maybe it jars your memory, like, oh yeah, this is the formula, that looks right. um, okay, so let's suppose that we lift a 100 kilogram mass 10 meters off the ground. How much work was done in lifting that mass? And here we have standard earth gravity, which will be 9.8 meters per second squared. Okay, so I need work is force times distance. This is mass. This is distance. So I've got distance just kind of given to me right away. I have mass. I need force. Or I'm sorry, I have distance. Yeah, I have distance. I have mass. I need force. And F equals ma. Or it's going to be 100 kilograms times 9.8 meters per second squared. So this gives me what? 980 kilograms meters per second squared. And again, we said that that is kilograms meters per second squared is a Newton. So this is 980 newtons for the force. So we have to apply a force of 980 newtons over a distance of 10 meters. And this gives me 9,800 Newton meters. So not too bad, right? Just the kind of basic algebra problem. We have this kind of discrete nature to this problem that we're applying a constant force over this distance. So we just have to multiply things together. How much work is done in lifting a 20-pound, which we're thinking of as a force, weight 8 feet off the ground? This is distance. We're given force. Again, work equals force times distance, or this is 20 pounds times 8 feet, or this is 160 foot-pounds or pound-feet. So we have to exert 160 foot-pounds of work to lift this weight. As a side note, you might notice that the Newton meters or foot-pounds, this kind of feels like a statement about energy, maybe. And that's kind of what the work energy theorem says, is that kind of the total energy at the beginning and the end ought to be the same. And at least in situations like this, kinetic energy and potential energy should kind of balance out. So so the work energy theorem relates kind of kinetic and potential energy at one point to the same at a later point. Okay, so where does calculus come into play? Well, what if instead of having a nice constant force applied over a distance, what if we had a varying force? What if I was, pushing some block and I was pushing harder at some points because maybe it was moving over a rougher surface, and pushing easier at other points because it was moving over a smoother surface? How would I figure out the total work in moving that block over that distance or picking up this weight over a certain distance when the force is not continuous? Well, if over a distance, if I have a force that's just constant, work equals force times distance, no problem. if I imagine over this distance, maybe I have two regimes. Maybe I have an area with a little higher friction. I have to push a little harder. I have to exert more force for a little while. And then maybe I have a slippier surface. I have to exert less force there. I see I can really just figure out how much work that I do in this first bit. I can figure out how much work that I do in the second bit and just add them together. Or this is going to be force 1 times distance 1 plus force 2 times distance 2. So if I have a piecewise constant force, I can just kind of split things up this way, right? I can just make a bunch of little regimes that look like this, add up all of the contributions, and then that gives me my work. What if my force is continuously varying, though? What if I have a force curve that looks like this? Well, the idea is an idea that we've seen before. First, I'm going to split my distance into n subintervals, where I'm typically thinking of n as a fairly large number. Each of these subintervals has equal width delta x, and I'm typically thinking of delta x as a small number. So I have a large number of subintervals that are fairly narrow for each one of them, or a large number of individual little distances I have to push over. And if the number of such distances is large and the size of each distance that I have to push over is small, then I can approximate the force that is continuously varying over that whole time, but I can approximate the force on each little subinterval by a constant, by just a constant force. And I know how to handle a constant force or even a set of a whole bunch of individual constant forces. So in other words, I can break this distance into a bunch of little subintervals. On each subinterval, I'll estimate or approximate the force as being constant. This gives me a bunch of little contributions to work. And then the total work done will be approximately the sum of these individual little bits of work done. And this can be approximated by, we'll call it, say, Fi, the constant force that we're using to approximate the force function on the ith interval, times delta x, the width of that interval, the amount of distance that we have to apply that force approximately over. So what I just said was what I have written here. So we want to sum I equals 1 to n of each little contribution of work wi, which is, say, f of xi delta x. We really could use any point in each of these subintervals. I'm just picking f of xi here as one of the points. And at this point, we have an approximation, which is nice. To the actual work that we want to find, we have an approximation in this sum. But I actually want to find the real answer. And so if I limit as n goes to infinity, delta x, the width of each interval goes to 0, the number of intervals goes to infinity, then I recover this nice smooth curve in the limit. And in the limit, my summation turns into an integral. So we have another formula for work, where work is the integral from the start to end point of force. And of course, this is completely consistent with this definition of force, right? If I just integrate constant F, say from 0 to D, then I just have big F, just a constant, times D minus 0. That's just work equals force times distance. So this is a generalization of the nice constant force structure to a structure where we have a varying force like this one, in particular, continuously varying force. Now, one little note about this, we might think of work, we might think of it as, or force as being kind of like maybe only a positive function or something like that. But this is really sign. So as Walter Lewin has said, funny physics professor that you can find his lectures online. He says you can get very, very tired while doing no work. So in other words, if I'm, sitting here at my desk and I decide, okay, I'm going to go out and run a couple laps around the block. Well, if I run a little bit and I kind of go uphill, and then I run a little further and I go downhill just as much, if I come back to where I started, neglecting maybe some things like air resistance and so on, I've effectively done no work. Or if I go to the gym and I take a weight bar with weight on it and I push it up and lower it down and push it up and lower it down and then rack it where it started, again neglecting small things like air resistance, I've done no work. I've gotten very tired. But kind of what's the idea there? Well, like you could imagine that I hook some kind of like, I don't know, something like a regenerative braking kind of system, some kind of generator or something to this weight. And when I push it up, I'm exerting a lot of effort. But when it comes down, when it comes down, it just kind of tugs on that generator and kind of spins it up and charges a battery. And then when I push it up, the energy that's stored in that battery could, in theory, be used to run the generator like a motor and help me push it up. And so I could, in theory, push this up and down a whole bunch of times and really not put forward a lot of effort. Now, just because I'm choosing not to capture that energy in a way that maybe is kind of useful for me in the future, that doesn't mean that something doesn't happen to that energy. So, that might make a little bit of this make more sense, is that when we're doing work like this, we could kind of, in theory, be capturing some of that energy to use later on. So if I lower something down, the gravitational potential energy gets less, but I could have, attached a pulley to that and attached that to a generator and charged a battery with that. And then later on, I could use that energy to kind of pull the thing back up to where it was before, if everything worked with 100% efficiency and so on. Okay, so let's look at an example. A force of 10 newtons is required to hold a spring stretched from its natural length of 5 centimeters to a length of 12 centimeters. Let me shuffle my papers over here. I need to. Yeah. And the question is, how much work is done in stretching the spring from 12 centimeters to 20 centimeters? For this, we'll use Hooke's law. We'll assume that the spring over this regime that we're interested in approximately follows Hooke's law. And Hooke's law says that the force applied by a string stretched x units from its equilibrium is f of x equals kx. We'll think of x in meters, and then the units of the spring constant are this kilograms per second squared. So I have f of x equals kx, and here x is meters from equilibrium. Note that F is a signed quantity. If we have a spring that likes to be here, say at its natural length, x equals 0, if we stretch it this way, then it's going to apply a force backwards. And if we compress it, it's going to apply a force back towards x equals 0. So if we compress the spring, it's going to apply a force in the other direction and vice versa. So the spring always applies a restorative force. It tries to get back to equilibrium. Of course, if you don't go so far that you stretch the spring out. So let's see, if we go, its natural length, its equilibrium position is 5 centimeters, and we're going to 12 centimeters. So we're going from my spring's natural length at position 0. This would be the end of the spring at position 0 is related to 5 centimeters total length for the spring. We're going to stretch it to 12 centimeters. Oh, wrong side. So we're stretching our spring to 12 centimeters, which is going to be at position x equals 7. And this gives a force of 10 newtons. So in other words, what does this mean? F of 7, or K times 7, and constant really quick here that I have to deal with. This has got to be 10 newtons. And I've got to be careful. This is 7 centimeters, so 7 times 10 to the minus 2. Or 7 over 100. Yeah, so that's correct. No, I want everything to be in units of meters. So 7 centimeters is 0.07 meters. Or this tells me that K is 100 times 10 over 7, or 1,000 over 7. Okay, so now my question is, if I now go and stretch the spring from 12 centimeters to 20 centimeters, then how much work is done? So if I'm out here at 20 centimeters, I see that this is 15 centimeters stretched from its natural length. So x is 15 times 10 to the minus 2 meters. So I'm going to integrate from, what is this going to be? From x equals 0.07 to 0.15 meters. I'm integrating force, f of x equals kx, where this is k. Again, I'm integrating force, and then the kind of times distance bit is taken up by this dx. If we check our units, so the spring constant is in kilograms per second squared. This x is in meters, so kilograms meters per second squared. And what was that? That was newtons. A little more room here. So this is newtons. work should be in Newton meters. Where does that other meter come from? This dx actually has a unit, right? This dx came from, where is my picture over here? Came from this delta x, the width in the distance direction. This delta x has units of meters. It has units of distance. Delta x has units of distance. Dx actually does carry a unit with it. So that's something to just be a little aware of, that our infinitesimals, this dx, for instance, does still carry a unit. So this dx unit is meters. So we are still, we do end up in Newton meters. We are still in the correct units that we expect. So that's a good check. And we can say, now we have what? 1000 over 7 times x squared over 2, integrating that from 0.07 to 0.15. That's a 7, not a 2. So this is 500 over 7 times 0.15 squared minus 0.07 squared, whatever that turns out to be, but this would be the exact answer. So kind of a lot of work, pun intended, to be done here. We had to use this first bit here along with Hooke's law to figure out what the spring constant K was for this particular spring with this piece of information. And then we had to apply that work function, that force function to find the work. We had to apply that over this distance, over this length of spring, which we had to translate into deviation from equilibrium using our work equals the integral force. So this is the kind of problem that that physicists love and mathematicians hate, because there's tons of units and tons of, like, wait, are we dealing with the distance from equilibrium, or are we dealing with the whole total length of the spring? So just lots of things to be careful about here. As Feynman would say, Richard Feynman, physicist, he was always good with quips and things. He'd say, physicist goes to a mathematician and says, like, hey, can you help me solve this problem? And the mathematician comes back the next day and says, here's the problem, and here's the solution in an arbitrary number of dimensions. He's like, what? I only need 3 dimensions. Like, why can't you just give me the solution in 3 dimensions? Like, well, just put in n equals 3, so just different perspectives from different fields. But I tried to stick with because this is a physics application, with kind of the physics way of going about a problem like this. And, length of spring is kind of a natural thing to actually measure. And then we have to translate that to distance from equilibrium. We have to translate that into the right units of meters and so on, because, if we're measuring this spring that's this size, we're probably going to use a ruler with centimeters, and we have to just be careful with units and all that. So, so a little unlike a lot of the problems that you'll see in Calc 2, but there's a problem or two like this on the homework, and just be careful about all those little details. So be careful about things like making sure the units are all kind of in a consistent unit, that you're using things like the equilibrium length is the length of the spring, but what's the deviation from equilibrium is what Hooke's law uses. So just make sure to keep all of those details straight. Okay, so our last example that I plan to do today in work. How much work is done in lifting an 80-foot rope weighing half a pound per foot to the top of a building 100 feet tall? And to make this a little more clear about exactly what I'm talking about, so suppose that we have a building over here. This building is 100 feet tall. We have a rope hanging over the building, but it's hanging like this, right? So this rope is 80 feet long. So it's not like we have the rope bundled up at the bottom and we just like pick the whole thing up and carry it up a bunch of stairs or something. But the idea is we're standing up here and we're going to pull this rope up to the top of the building. Now we might be tempted to just say, okay, well, what's the weight of the rope? The weight of the whole rope, 80 pounds at half a pound for a foot. Per foot, it weighs 40 pounds. We have to move it 80 feet or something like that. Well, 40 times 80, and we're done. But note that, remember that pounds is like force, right? So like how hard do I have to pull on the rope to pull it up to the top? Well, when I start pulling the rope up, when there's a lot of it hanging over the side, I do actually have to pull up really hard. And I have to pull up the same way that if I was, say, had a 40-pound dumbbell that I was lifting off the ground, I have to pull just as hard when I start pulling the rope up. But, let's say that I got most of the rope up here now, and there's just a little bit hanging over. There's just, 2 feet hanging over. Well, now I only have to apply like 1 pound of force to get that next little bit of rope up. So the force that I have to apply to the rope actually varies continuously as I pull it up. The further that I get, the more rope that I pull onto the top of the roof, the less hard I have to pull, the less force I need to exert to move the next little bit of rope up. So let's take a closer look at this. So how could I imagine pulling this rope onto the roof? How could I discretize this? How could I take this continuous process and do something along these lines, cut it up into a bunch of little pieces to try to analyze what's happening? Well, what I could do is I could look at each chunk of rope. I could take a chunk of rope of size delta X, another one. I could cut my rope into, metaphorically speaking, into 10 or 100 or 1,000 little chunks. So I could have an ith chunk, say here. That ith little chunk of rope has distance delta X. It's a, 1 foot or half a foot or something little slice of rope. It has some weight. And then I can imagine just kind of on like telepathically or something, like lifting that little chunk of rope in isolation up to the top. So I have kind of a first little chunk of rope that doesn't really need to go very far. I have a second that needs to go a little further. I have a third that needs to go even further, and so on until I have my nth bit of rope needs to go all the way up to the top. So what do I need to do? Well, I need to move for my ith chunk of rope. It needs to travel xi feet, since we're using pounds and feet. And it weighs 0.5 delta X pounds. It weighs half a pound per foot. And it's a slice of rope that is delta X units long. So I have a force times a distance. The work that I need to apply to get that little chunk of rope up, if I imagine kind of slicing it off and hanging it in midair and then levitating it up to the top of the roof, would be force times distance. It would be 0.5 delta X. That's the force bit times the distance X, I suppose XI. Or this is going to be 1/2 XI delta X. My total work is going to be approximately the sum of all these little increments of work as I take each one of these little slices of rope, kind of hanging in midair. imagine levitating it to the top for this slice and this slice and this one and each of these. So it's going to be the combined amount of work that I need to do moving all of those pieces to the top, which is 1/2 xi delta x. And then again, I want to take a limit as n goes to infinity and as delta x goes to 0. So as my rope slices or rope slice size goes to 0 and the number of such slices goes to infinity, I then recover equality. The summation turns into an integral. I'm integrating from, well, this top bit of rope. As I take the limit, it really just needs to travel 0 distance. So this very top little segment of rope here needs to travel 0 distance to get to the top, all the way down to this bottom bit. Again, as I take the limit, that bottom segment of rope gets closer and closer to 80 feet away from the top. So that lowest segment in the limit is going to have to travel 80 feet. One half x dx. Let's check units and kind of cross our fingers, hope everything works out right. So what's 1/2? That carries a unit of pounds per foot. X is distance, so feet. And again, remember that dx really comes from this delta x. That delta x really comes from the length of a little chunk of rope. It carries a unit as well. It carries a unit of distance or feet. These feet divide out, and I have foot-pounds, which is exactly the unit that I expect. So it looks like my units work out. It seems like I'm on the right track here. And then, of course, I just need to carry out the integration. Maybe we'll do it in blue because red is looking a little bit harsh or angry or something at this point. So if I integrate, I get x squared over 2, so 1/4 x squared, evaluated from 0 to 80. The integration is not the hard part here. It's really the getting everything set up. And this gives me 80 squared over 4, or 40 squared, or 1,600 foot-pounds. This is the amount of work that I do in pulling this rope to the top of the building when it's hanging over like this, pulling it up hand over hand. I do 1,600 foot-pounds of work. Are there any questions so far? Any questions on where any of the pieces came from here, or why I chose to set anything up the way that I did?
Was that accounting for the fact that it was only being lifted up halfway?
So we're still on the first part. So but good.
Oh, gotcha.
Good eyes.
All right.
No, good eyes. Yeah, so that's going to be the next question is, what if we only wanted to lift it halfway up? Okay, but any questions on the first bit here? Okay, so now, yeah, so excellent question is, what if I wanted to lift it only halfway up? And just to be clear what I mean by that, maybe I'll draw this one next to the initial one. I have my same 100-foot building. As an aside, it doesn't really matter how tall the building is as long as the height of the building is taller than the length of the rope so that the whole rope is hanging. We will actually look at, this will probably be in the supplement because I don't think we'll have time for it. We will actually look at an example where, what if I had a 50-foot building and an 80-foot rope hanging over? So like, say 30 feet of it is kind of coiled up on the ground. How would that change things. But if we go back to these first principles, how things were set up, we can really attack a much broader range of problems of this type than just kind of taking the entire rope that's hanging over a building that's taller than the length of the rope all the way up to the top. So that's what this question here is looking at. So what if I have my rope let me actually draw that a little bit closer, 80 feet, and I want to lift it up so that I end up with 40 feet of the rope kind of coiled up on top of the building, and then 40 feet hanging over the side. I guess that doesn't really look like a 2-to-1 ratio, maybe something more like that. So this is the idea. I want to pull the rope up and keep pulling it up until I have 40 feet on top of the roof, and then I'll just stop, and I'll stop there and measure how much work I've done. I might want to just come down here and say, well, I mean, can I just do 40 instead of 80? Like that should work, right? Well, let's be a little bit careful. Let's go back to first principles and ask what's happening. So if I imagine splitting my 80 feet of rope into some different slices, so kind of what happens here? Well, this slice does end up coming all the way up to the rope, up to the top of the roof, this top slice of rope. This kind of next slice of rope down comes all the way up to the top, this third one down up to the top. But say this slice here, it doesn't go all the way to the top of the roof. It goes to a bit below the top of the roof. This one goes to a little more below the top of the roof. This one, a little more. So kind of what do I have here? I really have two components to this problem. And I am going to take a little bit of time to draw out these pictures, or, a few different pictures. So really what it seems like I have is I have a chunk of rope, this top 40 feet, that is acting like this example over here, where I have a 40-foot chunk of rope that I just need to get all of it onto the top of the roof. That's this chunk here that's going to eventually end up coiled up on top of the roof. This has to go on top of the roof. And then I also have another chunk of 40 feet of rope. It's not on the ground. It's kind of levitating here. And what happens to this chunk? Well, this chunk ends up here, right? This whole piece just got translated straight up to there. It just got moved 40 feet higher. The top point of this rope got moved 40 feet higher. 12 inches down on this rope got moved 40 feet higher than it started. The very bottom of the rope, 40 feet higher than it started. There's really no difference between this and just, some big mass, a big cannonball or something that's attached to the bottom of the rope. Just being moved 40 feet up. This is just a dead weight of rope. This bottom 40 feet is just a dead weight of rope that we're just moving straight up 40 feet. Or another way of thinking of it is the contribution of this bottom 40 feet of rope to how hard you have to pull on each pull. This contribution never gets smaller. From the first foot that you pull up to the 39th foot that you pull up, it's still this whole second 40 feet, this whole bottom 40 feet is still completely hanging off of there. You still have to pull that each time. It never makes its way up onto the roof and kind of relieves some of the strain. But that does happen with the top 40 feet. So we have two components to our work here. We have one component that really was exactly this problem, 40 feet of rope hanging from the top and so on. So we really can use the same structure down here. That's okay to do, but it only takes into account this bit here. Now, I like setting it up this way. There are different ways you could set it up. You could set it up kind of under one integral and think of what is the force at each point, but I think it's more natural to set it up this way. But if you like to go a different route, you certainly can. This bit over here, I have a constant weight, a constant force that's being applied. That whole 40 feet of rope that weighs 20 pounds is pulling down over this entire distance. That force doesn't increase or decrease over this entire distance. This is just a basic force times distance problem. We don't even need calculus for this bit. This is just a force of what? 40 feet times 1/2 pound per foot over a distance of 40 feet. The 40 feet up here is the length of rope that I'm dealing with, and the 40 feet over here is the distance that I need to move it. So this is what, 20 times 40 is just 800. Pounds per foot times feet is pounds, times feet again is foot pounds. So this checks out, and we've already checked the units on this one, so I think we're confident with that integral. Or this is going to be x squared over 4 from 0 to 40 plus 800. That's 40 squared over 4, or 20 squared, or 400 plus 800 is 1200 foot pounds. Something else that we notice is that pulling the rope halfway up uses quite a bit more than half of the work to pull the whole rope up. Because pulling that last 40 feet up, the rope doesn't weigh too much at that point. I don't have to heave on it too hard to get it going. That last 40 feet, pulling it all up to the top, if I wanted to finish the job, it doesn't take much effort. It was really that first part where I have to really pull to get every foot up for quite a while. That's the much more effortful part. And that's that first half, moving it to 40 feet, we can see uses 3/4 of the total work of getting the whole rope up to the top. Okay, so